friends, welcome back to our channel EASI. Everything about semiconductor industry or everything that you need to know about semiconductor industry. So today we are going to talk about reliability, where we will understand the failure mechanisms, the testing procedures, and its long-term impact in advanced semiconductor devices. So without any further ado, let's get started. What is semiconductor reliability? Semiconductor reliability can be defined as the probability that a device will perform as intended for a specified period of time without failure under a given condition. So the reliability failures can be categorized broadly into three. The first one is the intrinsic reliability failure. These failures are due to the fundamental physics of the semiconductor material and design and is not caused by the manufacturing process. The next is, of course, the extrinsic reliability, which is driven by the manufacturing process, like the defects, particles, voids, or contamination during the fabrication process. And the third is called the system reliability, which is a combined reliability behavior of multiple chips working together in a system that includes packaging and interconnect. From reliability perspective, device life cycle can be best explained by a bathtub curve, where the life cycle is divided mainly into three phases: early life for infant mortality, useful life or random failure phase, wear out or aging phase. Early phase is the phase when the defects from manufacturing starts to surface quickly. Burn-in is usually the best way to screen this out. Next is the random failure phase. This is the phase of low and stable failure rate. Most of the product lifetime occurs here. This is where MTTF, or the mean time to failure, is measured. Lastly is the wear out phase, where the cumulative damage from EM, TDDB, hot carriers, and thermal cycling tend to cause rise in failure rates. Now, let us cover each of the failure mechanisms of wear out phase. First is the electromigration, or EM. So what is EM? Electromigration is the gradual displacement of metal atoms in a conductor caused by the momentum transfer from electrons to metal ions. It is a leading wear out mechanism in copper or tungsten interconnects. Root cause: high current density driving metal atom migration in the direction of electron flow causes electromigration. As an effect, either voids are formed, causing open circuit at one place, or hillock growth are found at other, causing shorts in metal lines. Metal interconnects, especially the narrow lines at the advanced nodes like the sub 5 nanometer nodes, are usually the most affected layers. As it is driven by higher current density, mitigation routes include limiting current density, copper alloys, barrier metal optimization, and adding redundant vias. Next, let's talk about TDDB, that is time-dependent dielectric breakdown. TDDB occurs when the gate dielectric, that is the oxide or the high-K material, gradually degrades under electrical field, eventually forming a conducting path, thus leading to catastrophic gate oxide failure. The mechanism involves trap generation within the oxide. As traps accumulate, a percolation path is formed leading to hard breakdown. The driving factors are electric field, temperature, and definitely the oxide thickness. It worsens at thinner gate oxide like less than 2 nanometer. As a mitigation, oxide or silicon dioxide is replaced with high-K material like hafnium oxide. This allows physically thicker films at same equivalent oxide thickness or EOT. Thus, it reduces TDDB. Testing includes both time zero breakdown and TDDB at stress, that is at elevated voltage and temperature, to extrapolate the lifetime. Soft breakdown means partial leakage path which is recoverable, while the hard breakdown is the formation of a permanent conducting path through the oxide. Weibull plots are used to characterize the TDDB distribution. Next, let's talk about HCI and NBTI. HCI, or the hot carrier injection, is a mechanism where the energetic carriers like the electrons and the holes near the drain gain sufficient kinetic energy to surmount the silicon and oxide barrier. Trapped at the oxide interface, this leads to threshold voltage shift and transconductance degradation. It is more severe in NMOS, which worsens at shorter gate lengths. Mitigation includes drain engineering with partial self-healing occurring at higher temperature. Next is the NBTI, or the negative bias temperature instability. NBTI occurs in PMOS under negative gate bias at elevated temperature, caused by trap creation at the silicon and the oxide interface, leading to VT shift and degradation of drive current or ion, thus impacting the device performance. It worsens with temperature and can be partially recoverable by duty cycle management. So today we talked about different reliability failure modes like EM, TDDB, HCI, and NBTI. In our next sessions, we will talk about the reliability risks our future nodes are going to face with different monitoring options. With that, we have come to an end to our today's session. Please like, share, and subscribe. See you in our next session. Till then, stay safe and stay healthy.